Hi, everyone. So I'm going to go ahead and get started. My name is Francheska Figueroa, and I am with Arizona State University. I am going to share with you a bit about a research grant that I have been privileged to be a part of. It's called Accessible Computational Thinking, CT, in the Elementary Science Classroom, using a culturally and linguistically responsive context. I am joined by two of my colleagues, Dr. Ebony Terrell Shockley, who is with the University of Maryland. She is a co-PI on the project, and Lynn Yan, who is also at Arizona State University, and she is a graduate assistant and PhD student. Okay, so here is our research team. We have 6 researchers from the University of Maryland, and we have 7 researchers from Arizona State University. So we are a rather large research team, but we have been meeting collaboratively for a little over a year, and we have worked via Zoom and have actually met each other in person a couple of times. So it's been a privilege to be a part of this team. So here are our content and language objectives for today's session. Today, we will identify how CT is accessible in the elementary science classroom using a culturally and linguistically responsive approach. Our language objective, today we will listen for examples of how computational thinking and culturally and linguistically responsive teaching is made accessible in the elementary science classroom. So I'm just going to give you a bit of background about the project. So when we started the project, we individually came up with ideas of a framework that we might consider using science, computational thinking, and culturally responsive teaching. We came to consensus with the animated framework that you see on the screen. And so really the way the framework works is we have the foundation in elementary science, and teachers have the opportunity to really create their lessons using one of 2 ways. So they can either, all teachers will start with elementary science because we have been working with teachers from grades 1 through 5, and they can either integrate computational thinking and from there integrate culturally and linguistically responsive teaching, or they can start with culturally and linguistically responsive teaching and then integrate computational thinking. So there is not just one approach of how to create these lessons, but the idea is at the end of their lesson planning and the final product, they will give students opportunities to engage in science using computational thinking around a culturally and linguistically responsive teaching pedagogy. By accessible computational thinking, we know that computational thinking is ubiquitous in modern science. We know that it is rarely integrated in elementary classrooms. It is typically integrated in middle school and high school. We know that there is an inequitable distribution of computing in pre-K and 12th grade setting. We also know that if there is early access to computational thinking, we will reduce the lack of diversity in STEM fields. So we really want to make sure that we are making computational thinking accessible to teachers using new technology at times, so they can in turn make it accessible to their learners. What are the goals of the project? Well, we first are asking teachers, or we have asked teachers to describe and consider the importance of expanding computing participation. We have asked teachers to create lesson plans for the academic year, where the lesson plans have integrated computational thinking, culturally and linguistic responsive teaching around a science lesson. And then the team will go into classrooms and collect data based on observations of lesson delivery. Year 1, which began really with the 5-day summer workshop, we asked teachers from 2 districts in the Phoenix metropolitan area to join a 5-day summer workshop, which we implemented in the first week of June. We had 24 teachers, and we asked teachers to create a lesson that they will deliver during the academic year. Researchers from the team will go into the classrooms, collect data from the observations, and we will also include during the academic year an online learning community. But we will give teachers opportunities to discuss and provide support from the research team, but we will also give teachers opportunities to peer support one another. Year 2, we will have a 3-day summer workshop, and again, during that academic year, we will provide coaching observations and an inquiry support group using an online learning community. So I'm now going to make a connection between the SciOp model and an additional framework that we created for our research, the framework for teachers' integration of culturally responsive teaching into elementary science. So we know the SciOp model, Sheltered Instruction Observation Protocol, has 8 components around 30 features. And what we created is a framework for asking teachers to reflect on their own cultural lens. So this is really a diagram of a lens, and in the center we have culturally responsive teaching. Around culturally responsive teaching, we have 3 opportunities: equitable instructional practices, student-centered content, and inclusive relationships and communities. From there, we included additional items or responsibilities as teachers that we would hope to see in a classroom using CT and culturally and linguistic responsive teaching. So what I've done is I've made a connection to the SciOp model. So if we look at the first opportunity, equitable instructional practices and modeling high expectations, I connected the SciOp model with the 8 components and 30 features, because I know if I am a teacher using the SciOp model with fidelity, then I am modeling high expectations for not only my multilingual learners, but for all students. Draw on students' cultures to shape CT and science practices in the classroom. I made a connection to building background and interaction. There's a seamless connection to building background, but you might consider, what does interaction have to do with this feature or this section? Well, if we think of the 4th feature of interaction, asking students to use their primary language to offer a level of support during instruction, we can look at that as culture. Language and culture are one and the same. Our next section or opportunity, student-centered content, incorporate student experiences to promote respect for differences. I could say with this section, we could include the 8 components and 30 features, but I added lesson preparation and building background. Bring real-world issues and experiences into the classroom. That's a seamless alignment. I don't think I need to explain much on that. And so inclusive relationships and communities. So honoring multiple modes of sense making and expression. So when I think of multimodalities, I think of the SciOp model. I included comprehensive input, strategies, interaction, practice, and application. We know with these 4 components and with the 8 components and 30 features, I am going to honor multiple modalities so I can give my students opportunities to engage in learning through whatever sense making and expression they need to access the content. And last, we have interaction aligned to collaborate with families and local community. Again, I thought of the 4th feature of interaction. Speak up about and respond to prejudice, bias, and stereotypes. I would say the SciOp model. If I am a SciOp modeled teacher and I'm using the 8 components and 30 features, then I am a culturally and linguistically responsive teacher. Ebony?
Thanks, Francheska. So culturally responsive teaching aligns very well with Sheltered Instruction Observation Protocol. As you can see, this definition from Dr. Geneva Gay, this is from her recent 2018 text, describes culturally responsive teaching as having the following: that we, educators, researchers, scholars, community leaders, activists, acknowledge the legitimacy of the cultural heritages of different ethnic groups, different racial backgrounds, their legacies that affect their dispositions, the attitudes, the way they show up in school, their approaches to learning, and that we take that content and those experiences and those dispositions as worthy to be taught in the curriculum. That we build bridges between home and school experiences, and we're going to see a little bit more of that, as well as between academics and lived sociocultural realities. So both in formal and informal spaces, we are being charged with connecting home and school experiences. We're building safe spaces and we're building culturally responsive spaces for our learners. And that we use a wide variety of strategies connecting students to learning. So how are we going to build a bridge? How are we going to expand our pedagogical tool belt to include learners from linguistically diverse backgrounds, learners from underserved backgrounds into our classroom, and how are we going to center them and praise not only their responses, the way that they show up, their traditions, but also each other's. And so thinking about culturally responsive teaching in science, it's really important for us to consider how we framed our own understanding of science and who can be a scientist. And a search engine revealed not so long ago these images for scientists. So you have to think about, the algorithms that had to be used to come up with these images, the thinking behind these images, why these images, what systems, what mindsets, what dispositions did the individuals who formulated these images to come forward or to present for scientists. Do you see someone who looks like you? I don't see anyone who looks like me. So what that does is sends the message that someone who looks like me, for example, or potentially you, depending on your phenotype, is you can't be a scientist. There's no representation of you as a scientist. And what that looks like, not just in an ESOL classroom, but what that looks like in any classroom which is fed from the internet or from the media is problematic. Or you could counter that narrative with other images that are representative of a wide range of backgrounds. And so thinking about that home to school connection and thinking about those images brings us to funds of knowledge. So funds of knowledge, we frame a lot of our cultural responsive teaching in funds of knowledge. Cultural responsive teaching preceded funds of knowledge, but these cultural anthropologists went into households, Spanish-speaking households, and really began to unpack the ways in which those families engaged. And their findings and our work as culturally responsive educators show that when we consider and when we build those bridges from home into school, considering their languages, their dialects, then students understand that it's almost like flipping the classroom, right? From a linguistic diversity background, perspective, we find that bringing those practices into school helps students with feeling, again, safe, feeling seen, being heard, allowing them to speak, allowing them to make mistakes. Finding out, well, what are those misconceptions in science or in STEM in general? And then how are you going to help students reason their way to a right answer, considering their funds of knowledge, considering those bridges, and how can those be assets? How can we see those as assets and not deficits? Okay, so this is funds of knowledge. So we know that our culturally responsive teaching frameworks, we know that those funds of knowledge dispositions carry into literacy, okay? And in elementary schools especially, oftentimes there's not even a space or a block for science. So understanding students' dispositions is important no matter the content area, but we know that reading, writing, speaking, listening, those domains of language, that literacy carries over into science. And so we have here a way for educators to capture the habits of mind, the dispositions of students, to build those bridges and create culturally responsive spaces. So to your left, you will see, this is a Garfield image. I joke all the time that the students at least in PK-12 might not know this character, but this is a fun and well-researched way to tap into your students' understanding. So for example, this is just a snippet from this particular article. How would you feel if your teacher asked you to go back and change some of your writing? Finding out something that seems so simple. How often do we switch papers in class? When we're writing, when we're doing the composition process or engaging students and some sort of feedback. Well, understanding whether students actually are okay with that is one way to consider their dispositions, which is being a culturally responsive teacher using data that you've gathered from the students. And that's just one question. There are more questions on this document, and there's also one specifically for reading that you can look at. It is called the Reading Attitudes Inventory. So please consider it as you're creating and enhancing your culturally responsive space for diverse learners and for all learners. As well, we have a document from the National Science Teaching Association. This particular resource was in the Science and Children publication. And here we're asking students to rank each item below, with 1 being favorite and 14 being your least favorite. And you may decide as you're thinking about your students to use pictures and allow them to draw and bring in some of their other skills to this particular document. So feel free to adapt it. But we have weather, we have plants, we have animals, we have space, we have rocks. Considering what students like, considering their interests. And then maybe you can group students based on interest and not just based on skill. So these are 2 resources that we really want you to think about, that I also want you to think about, and that I have used in the PK 12 space, as well as preparing teachers. Do you like science? Please say yes. But why or why not? And so these are resources, like I said, that you can use and that you can adapt in both literacy and science, and trying to bridge those together. All right, so I want you to do number 1, number 2, or number 3. Identify or describe an artifact, consider languages, sounds, or exchanges that make you feel safe, and then what would you have liked your least inclusive teacher to do? Whichever one you do, write down your answer and think about how you can bring that into the classroom. Consider students who are like you, and consider students who are different from you, okay? For the purpose of brevity, I'm going to keep going. All right, so I mentioned in the Google Scientist document or slide that for me, I did not find a mirror. I did find a lot of windows. And what Dr. Rudine Sims Bishop states is that windows are an opportunity for a reader or a student to look into the world of others. And that's fine, but we also want mirrors for our students. And so mirrors and windows has continued into the 21st century. And you can see some data here from the lack of diversity in children's books in 2015. You can see students of color are less represented than animals in trucks. And in 2017, you will see that students who are exceptional have the least numbers in terms of representation. And so thinking about the language support, bridging literacy, and multiple forms of representation is really critical for culturally responsive teaching. There is a video that we're going to link in our resource page here so that you can review it. And it really brings to bear what equity means in culturally responsive spaces and in computer science or computational thinking spaces, which my colleague is going to
factors that go into equity
present for you. And finally, our culturally responsive framework, again, for you to think about. Please take a look. Please reflect. Thank you.
Thank you very much, Francheska and Ebony. Hello, everyone. My name is Ling Yan. I am a second-year PhD student at ASU. Continuing the previous presentation, I'm going to talk about computational thinking. Particularly, I will introduce the definition of computational thinking, the reasons why we integrate computational thinking into elementary science classrooms, and the computational thinking models we are using in our ACT project. Up to now, I think we have mentioned a lot about computational thinking. And I guess you might be curious about what is CT, what is computational thinking? And here is the answer. Computational thinking refers to the thought processes that allow us to take a complex problem, understand what the problem is, and develop possible solutions. Computational thinking can be done with computers or without computers. And now, before we talk about why we include computational thinking in elementary science teaching, I am going to show you a video. As you watch the video, I would like you to think about the connections between computational thinking and science, and what words, ideas, concepts, or practices stand out to you.
We have to study the universe by using computers. We simulate a lot of the physical processes that happen in the universe. We bring it into our computers and we try to, as best we can, simulate what's going on out there.
Computing plays a central and crucial role in my research. Pretty much nothing that we do would be possible without computers. We use computers to collect data, to store, to retrieve data from online databases. We use computers to analyze those data. We use computers to visualize results and to try to gain insights. We use computers to model the systems and to make predictions. So it's at the center, it's in every single stage of our research.
It would be absolutely impossible to do anything in modern neuroscience without computational thinking and methods. Everything, basics of image analysis, basics of physiology, looking at mass spectra of proteins. None of those things would be possible without computational thinking. When
I started as a researcher, I had no programming experience whatsoever. When I was in high school, I didn't do any programming. When I was in undergrad, I took physics classes, I took math classes. Those were good foundations for trying to understand the field. But when it came to the actual practical aspect of doing research, it didn't really help there. It kind of left me in the dark. So I really wish that back in the day I had picked up programming, that I had picked up computational skills, that my classes incorporated programming and projects that involved doing these kind of things.
It would be completely impossible to do my research without computational tools.
For astronomy, both observational work, experimental work, and theoretical simulation work relies on computers and computational work to actually lead to new discoveries, new knowledge, new understanding, and make progress.
It would be absolutely impossible for me to do what I do without computational thinking.
The most important thing for a young student currently interested in sciences generally, I believe, would be to study computer science. If I had the opportunity to do it over again, that's personally what I would do.
Okay, as the video mentioned, computational thinking is ubiquitous in our society, changing the way we communicate, interact, and think in many fields, particularly in science. However, opportunities to learn computing often only emerge as electives in secondary schools and are inequitably distributed among students from different races, ethnic groups, and gender. Therefore, our project specifically focuses on supporting elementary school teachers in integrating computational thinking and culturally responsive teaching into their science instruction. We believe this change in teacher practices will support all students in developing fundamental knowledge, personal connection, and interest in science and computing. Okay, here is the computational thinking framework we are using in our project. The framework from previous grant, which was designed to support elementary teachers in understanding and using computational thinking in their science practice. The framework includes 4 practices, which are using data, programming, computational simulations, and system thinking. The first practice is using data. The practice involves collecting data with computational devices, finding patterns, and the relationships in data sets, sorting data, and creating graphs or charts. Data is not limited to numbers, but also can be images, text, or sound. When data is turned into information, it can be used to make decisions. Text and number data can be collected and organized to make it meaningful. For example, teachers can provide each student with an About Me worksheet to record data about themselves. For example, name, age, hair color, self-portrait, favorite pets, likes, dislikes, and the numbers of brothers or sisters. And then students can discuss ways to represent each type of data and then display the worksheet and use this to highlight and explain that. All of this information is data. And the second practice is programming, which involves breaking down bigger problems into steps individually, creating step-by-step instruction to solve a problem or perform a task, using a computer to write instruction in order to complete a task, and repeatedly using results from each attempt to modify the proposed solutions. The third practice is computational simulations, which involves using interactive applications that represent a scientific phenomenon to understand it or test different scenarios. The practice also involves comparing a simulation to real-world phenomenon it represents and discussing the limitations of computational simulations and how they can be improved. And the last but not least one is system thinking. This practice involves recognizing how parts of a whole can be represented with numbers, such as using Celsius degrees for temperatures and millimeters for rain within a weather system. The practice also involves calculating how parts of a system are linked in correlational and measurable ways, such as the decrease of prey in an ecosystem associated with an increase in predators. And the practice also involves determining how an increase or decrease in quantity in one part of system contributes to the increase or decrease of another part of system. So above is the computational thinking framework we are using in our project. Okay, and now let's revisit two important frameworks of our project. And now let's welcome Francheska to continue our presentation. Thank you very much.
Okay, so I'm going to wrap up with making an additional connection to the SIOP model or accessible computational thinking with the SIOP model. Again, we know the acronym for SIOP is Sheltered Instruction Observation Protocol, and I am by no means advocating that we change the acronym. I just wanted to do a play on words with a play on acronyms and make a connection between ACT and SIOP. So ACT with SIOP, accessible computational thinking supports multilingual learners through integrating science, CT, and culturally and linguistically responsive teaching by opening computing opportunities for all learners and populations. So I'll end with the content and language objectives. Today, we identified how CT is accessible in the science elementary classroom using a culturally and linguistically responsive approach. And our language objective, today we listened for examples of how CT and culturally and linguistically responsive teaching is made accessible in the elementary science classroom. I've also included a slide with an opportunity to contact the presenters. Here you have our email addresses. You also have the ACT website address. Please visit the website because we will make periodic updates to our research, and we will also include the final findings from our research study. So thank you for joining us. Gracias. Grazie, obrigada.